All right. Well, let's dive in for today. So, we're going to cover a really important topic today, and that is statistics. We'll also cover a little bit of data output. But hard to believe we're on day 8. I feel like we've come so far in the past 7 days, and we're about to, really dive into kind of I don't want to say like the take home product, right? But a lot of time when we're doing data analysis, data cleaning, data science, our ultimate goal is to, draw some novel insight. And so statistics is a huge part of that. So we're only going to touch the tip of the iceberg today, but we're covering things that, I think Carrie, Elizabeth, and myself, we use all the time in research. So there's certainly more complicated approaches that we could talk about, but we're going to cover kind of the essentials, I think. So let's get into it. All right. So a little bit to summarize from yesterday, we talked about data visualization, which I think is one of the more fun topics for a lot of us. And the ggplot function is going to be the heavy hitter for that. So inside that, we can specify what data to use and what variables will be mapped where, the X or the Y axis. Or, if we want to do any groupings, we can use the color argument inside that AES part of ggplot. To specify the mapping. We can add layers. So remember, ggplot is like a cake. We're setting things up with the base, but then we're adding the fun stuff, the points, the lines. Those are like your sprinkles and your toppings. So using functions like geom_line, geom_point. A lot of these start with geom_. And sometimes you'll see, some strange sawtooth pattern. Sometimes that means you need to add a group element to make it make a little bit more sense. So just paying attention to kind of the grouping of your data if that's present. Always make sure you're plotting what you think you are by checking the numbers. Remember, we can do those summarization and count tables and things like that just to verify that what we're seeing is what we think it is. Facets can also be a really nice feature to split up your plot if you've got a lot of data. We talked a little bit about factors and how they allow us to have different order from alphanumeric when we have categorical data. So things like small, medium, large, for example, we don't necessarily want those in alphabetical order. And so we can change data to be a factor using mutate and either as_factor or factor functions. So just kind of not changing the data necessarily, but changing how R interprets it by changing it from a character class to a factor class. And so that helps us reorder things how we want. All right. So today we'll talk a little bit about how R computes some basic statistics and fits some basic statistical models. We'll talk a little bit about correlation, t-tests, and then linear or logistic regression. And I promise we're not going to get too deep into the math, but we'll talk a little bit about some background just so you feel like you have the right context to talk about some of this stuff. And we're going to focus really on how R implements these tests. We're going to kind of gloss over some of the statistical theory. There's whole courses on statistics and just even building up to t-tests and things like that. And there's a lot of assumptions for statistical tests. And so definitely encourage you to, if you're exploring this more, or you're doing research or you're thinking about doing research on different topics, to understand, the assumptions that underlie your tests. And, not all of us have had a statistics class or have time to take one, but there's lots of resources out there to learn more about it, particularly Carrie's open case studies. We've got stuff on the resource page, but important to understand, how and why you're doing a specific test. And so anything we kind of demonstrate, we're not necessarily going to meet all the assumptions. For example, you want normality of your residuals in linear regression, and we haven't checked a lot of that stuff. So, when you go out and do this in real life, just be thinking about those things. All right, so let's talk about correlation first. So correlation coefficient, this is a summary statistic that's going to measure the strength of a linear relationship between two numeric variables. It's going to tell us a little bit about the strength of the relationship. So basically how well the points form a line. So this would be kind of like a strong relationship here, or perfect positive correlation. Everything sits nicely on a line. This is a little less strong. But then on the other end, we have a very strong, perfect relationship here. So it tells us about the strength, whether it's close to 1 or close to -1. And it also tells us the direction of the relationship based on whether those points are pointing upward, it's a positive relationship, or whether it's pointing down, it's a negative relationship. So I could imagine over here on this side where I have a positive correlation, maybe the amount of cute chihuahuas that I see. We have Penny is our an unofficial mascot, our favorite chihuahua. The amount of chihuahuas I see is positively correlated with my happiness, right? So that would be that relationship here. But maybe over here, the amount of rainy days is negatively correlated with my happiness. So I like to see the sun sometimes. So those are some examples of kind of where we might see correlation. And of course, feel free to check out more here. All right. So the function core is going to compute our correlation in R. There's lots of options you can add. So we'll talk about this in a moment, about using complete observations, and then about different correlation statistics that you can use depending on kind of your assumptions of your data. So typically with the core function, we're going to want to provide two numeric vectors. So we talked about this a little with taking like the means, doing summarization, that you can use the poll function to grab those. We'll talk more about that. Or you could provide a data frame or tibble with numeric columns. So basically we want numeric data for correlation. And by default, a Pearson correlation coefficient is computed. And so Pearson may have a little bit more assumptions compared to your Kendall or Spearman. So just looking into that more if you're curious about it. All right. So the core.test, so a little bit different, is going to just give you more information. So compared to core, it'll just give us that correlation coefficient. But core.test is also going to give us a test for association. So it's going to give us a little bit more information. So we provide and get all the same stuff as core, but we can also perform a test. So a two-sided test, meaning that the correlation coefficient is not equal to 0, basically like, is there a relationship or not? Because a 0 correlation would mean no relationship. So is it different from 0, or is it greater than 0, or is it less than 0? So we can test trying to say, okay, well, I see this scatter plot, but is there potentially a significant correlation here? So that would allow us to get that statistic, that p-value often associated with, trying to say something is statistically significant or not. All right. So our first gut check, what class of data do you need to calculate a correlation? We need character data, factor data, or do we want numeric data? Give us a few moments to get our answers in. Anyone else? What do we think? All right. Yep. So I agree. We want numeric data because when we're thinking about a correlation, typically, like in my head, I kind of imagine a scatter plot, right? And I'm trying to see how those dots line up on a line. And to do a scatter plot, I would need numeric data. So yeah, exactly. I agree. All right. So let's look at an example. We'll look at the data set of yearly CO2 emissions by country. I'm going to go ahead and bring this into R. So this is that data set that is on daisy.org. And it's got we've seen this one before. It's got different countries and tons of years of data, but there's a lot of missing data. So we go all the way to the end. We see a little bit more detail as far as those emission values go. All right. So let's create two vectors so that we can calculate a correlation coefficient. So let's create a vector 1980. And we're going to take that yearly CO2 data set. We're going to pull the 1980 column. And we want those tick marks because it is a number. So not the best formatting. And you'll notice over here, I put a Y in front of the object for a year because we can't have an object start with a number. That's not appropriate. All right, so stored those values. Let me also do 1985. So what I'm setting up here is a comparison between these 2 years. I want to see if they're correlated year over year. All right, and important to remember that like other functions, if there are NAs, we might get an NA or missing value as the result. But we could specify like, hey, if there's missing data, just don't use that line. Don't use that comparison. And so we'll get a correlation using non-missing data. So let's do core Y 1980, object 1, and then 1985. Okay, so I definitely have some missing data in there. So, if I even just take a look, I can see that there's missing values, right? So let's use complete observations, complete.obs. All right. So dropping the missing values, we get a correlation of 0.99. So do we think this is a strong relationship, or do we think this is maybe there's not any relationship between those years? What do we think? 0.99, pretty close to 1. Yeah, I agree. Strong positive correlation. And that makes sense, right? Because I wouldn't expect a country to dramatically change its emissions from, 5 years ago, right? So it makes sense, I think, that the years are pretty correlated. So probably if you had a bigger gap, maybe it was like 1900 to 1985, it would be a little less correlated. But yes, I agree. I think those are pretty closely related. Okay, so if I wanted more info, I don't just want this correlation coefficient. I could do core.test and get a little bit more detail. So same format. So if you remember one, maybe remember core.test because I think it gives you more info. So yeah, our T statistic, right? Pretty high. And so that corresponds to a pretty low p-value. And so, just as a reminder for our interpretation, typically anything smaller than 0.05, we consider that to be a significant relationship, right? So this is a very, very small p-value. So I feel pretty confident in rejecting the null hypothesis. So I feel pretty confident that the true correlation is not equal to 0. And again, there's my statistic here. And we also get a confidence interval if that's something that you're interested in. The Broom package can help make statistics look a little bit more tidy. So this is kind of like, it's fine, right? Like it's nice to look at in the console, but maybe I want it in kind of like a tabular format. Like I want it in a tibble. And this is just, this is text printed on the console. So it's not as well organized, right? Okay. So let's load up the Broom package and calculate tidy results. So taking core.test and putting that inside the tidy function. So let's load the Broom package. I already have this installed. You can kind of tell because it comes here in a preview. Loading that up. Let's call this core results. And we can save the results of core.test and then tidy core results. All right. So it's put everything in a tibble for us. It gives us the estimate of the correlation coefficient and the p-value. As we can see, that's pretty small. And then the confidence low, confidence high, and the method that was used. So organizes it a little bit more nicely. All right. And so anytime we're doing, a correlation examination, I'm personally like pretty visual. I like to create plots. And so if you were curious about doing a ggplot, you might incorporate some geoms and some other functions to make your plot look really nice. And so here, what I've done is done geom smooth to add a trend line and annotate to basically print the correlation coefficient onto the plot. So here, I've pulled out the estimate from the core result table that I made over here. So pulling out that statistic and saving that as a core value, and then adding that with my annotation, right? So basically creating a label here where I have pasted together R equals and then the core value, and then stick it onto the plot here. So using the annotation function, I want to annotate some text. I'll tell it the coordinates I want that annotation to appear on, and then I'll say what exactly I want that annotation to be. I want it to be R equals and the core value. So if that's of interest to you, definitely recycle this code as you like. And again, this is 1980 for 1985. Not a perfect correlation, but very strong positive relationship. All right. And sometimes we're interested in a correlation between pairs of columns or pairs of data. And so we can do that pretty easily, actually, as long as we provide numeric information. So again, we want numeric data, not categorical, not character. So we can compute correlations for all pairs of columns of a data frame, a matrix, or a tibble. So any of these kind of spreadsheet-like objects. And we often call this computing a correlation matrix. As I said, columns must be all numeric. And so what I could do is, say I have this yearly CO2 data set. And remember, I have some categorical data, right? I have the country in question. So I'm going to want to make sure that that's not in the data when I want to calculate that correlation matrix. And so what I could do is a handy subsetting here where I select just those columns that I'm interested in. Maybe we do 1980 again. We do 1985 again. And then maybe let's do 2000 and 2014. Okay, so I have all numeric data now. Let's save that as CO2 subset. All right. So the nice thing is I can just put that subset data directly into core and calculate that matrix, right? So I could see, all right, 1950 versus 2010 and find the statistic there. 1950 versus 1985, find the statistic there. So yeah, we can do multiple comparisons at once. Let's do core, CO2 sub, and we'll want to use complete observations once more. All right. So because I like to nerd out about this a little bit, 1980 and 1985 are pretty close, but actually kind of interesting is what we're seeing is like the farther apart the years go, that relationship starts to weaken a little bit. So 1980 versus 2014, the correlation of the emissions for those years starts to break down a little bit. So countries are starting to adopt different practices, maybe industrializing a little bit over the course of 30 years. So that makes a little more sense. All right. We love the core plot package because it can make correlation matrix plots, find these really just really nice visualizations. So pretty straightforward, only one function really needed here. Core plot, make sure I load that up, and then do core plot of that numeric subset of data. Let's see. I want to save the matrix first. So let me do that. And then plot that correlation matrix. And basically the bigger the dot, the more tight the correlation, and then the color will indicate the direction, right? Whether it's positive or negative. So this can be really nice if you're looking at a ton of numeric variables and you're just trying to look at like overall patterns or trends and see kind of what columns of your data perhaps are more correlated than others. All right. So word of caution is the correlation does not imply causation, right? So this is an example that we love to use comparing Lyme disease incidence. So this is a vector-borne disease carried by ticks, right? Lyme disease is pretty brutal, can cause long-term immune issues. And the number of fried chicken restaurants, and not sure, we don't want to advertise what fried chicken restaurant it is, but just suffice to say it's one chain of restaurants. And when we plot these against each other by state, we actually get a significant relationship. And so we have to be careful when we are interpreting this, that fried chicken restaurants are not providing some kind of immunity for Lyme disease, right? It's not actually a direct impact or causation on the disease incidence, but perhaps there's some other relationship or something else that may be causing this pattern, right? So I think this is maybe just a word of caution to think about your data and dive into it more. So there could be a causal relationship there, but oftentimes the story is a little bit more complicated. Okay, so that's correlation. Let's talk a little bit about t-tests. So when we're talking about t-tests, the common ones that you'll typically see are a 1 sample and a 2 sample t-test. And this is super jargony. So what does this mean? So a 1 sample t-test is typically used to test the mean of a variable for one group. So let's say I want to see that, like, how much these cute chihuahuas weigh, right? I want to see if the mean, the distribution of those weights is different from some value, right? I'm not comparing anything. I'm just trying to test if it's equal to or similar to some value. However, a 2 sample t-test would be used to test the difference in means of a variable between 2 groups. So maybe I was looking at the chihuahua weights from the state of California versus the state of Maryland, right? So comparing 2 groups together and seeing if the difference is 0. So yeah, 2 sample t-test, typically 2 groups. And if you have the same individuals collected at 2 time points, we could even call it a paired t-test, 2 sample paired t-test. So again, 1 sample is typically just 1 group. We're trying to test if that mean is different from some value. And 2 sample is comparing 2 groups. And the nice thing about how we do this in R is that the t.test function is going to be able to do both. And it's going to know based on what I provide it, whether it's 1 sample or 2 sample t-test. All right. So our one sample t-test, again, it's testing that the mean of a variable is different from some value. And so by default, these are our arguments. It's going to test whether the mean of a variable is equal to 0. So the alternative hypothesis is that the mean is not equal to 0. However, we could specify this value if we wanted to, right? We could say, I think those Chihuahua weights are not different from 10 pounds instead of 0 pounds. By default, we're going to use a two-sided alternative. So we're testing not equal to, right? It could be greater, it could be more, or it could be less. But if we specify, we could say, I think the value is greater than 10 pounds. I think it's more than that. So just depends on the test you want to do. By default, it's going to return a confidence level of 0.95, and it's going to omit missing values in the data. And so let's look at our CO2 emissions data again. I'm supplying a vector here, very important. All right, so let's do t.test of y1980. All right, so we're trying to say, all right, the emissions in 1980, that they are not equal to 0. And when I take a look at that p-value, I see, okay, it's, lower than 0.05. I feel pretty confident those emissions are not 0. So there we go. That one sample t-test. Our two sample t-test. So again, this is the difference in means of a variable between two groups. We're comparing state A to state B, or time A to time B. And so by default, we're testing whether the difference, so this is slightly different from one sample, we're testing whether the difference in means is equal to 0. So if that difference is 0, that means our groups are the same. But if that difference is quite large, that implies the groups are different, right? A mean over here versus a mean over here. The distance, the difference is quite large, meaning that those groups are different. By default, we're going to do a two-sided test. So it could be that group A is larger than group B, or it could be smaller. Either one is fine. We're going to assume a confidence level of 0.95. We're assuming that the data are not paired. I mentioned if you're doing different time points, the same, you're sampling the same test subjects over time. By default, it's not going to do that. So you can specify that though, if that's relevant to you. And we're assuming that the variance in the two groups is not equal. So if we're looking at a bell curve of values, they could be a little different in size. That's okay. And it's going to omit missing values in the data and encourage you to check out the case study here if you want more info about t-tests. So how do we do this? So let's go ahead and provide our 2 years that we were looking at before. So this was our one sample, and we're going to do a 2 sample. So we're testing here whether the difference in means between 1980 and 1985, we're testing whether their difference is greater than 0. And so when I take a look at that p-value, that's pretty high, right? It's not less than 0.05. And so what that tells me, and here's our confidence interval here, right? And that's 0 falls well within that. So I don't feel confident saying that these years are different, right? I would reject or fail to reject the null hypothesis here. So I think those means are there's not really evidence that they're not different. Okay, so just like that correlation, we can use the Broom package with the tidy function to get nicely organized results. So we did that up here. Oops. So let's take tidy t.test of 1980 and 1985 and get a little bit more cleaner results, right? So it's easier for me to extract that p-value as well as the confidence low and high boundaries. If you're running a lot of statistical tests at once, you are going to run an increased risk of type 1 errors, right? You're more likely to discover a false positive. If you're running tons and tons of tests, chances are you might get one by accident that is significant. And so you might want to do something called a p-value adjustment to account for that, right? You're doing multiple tests. You want to be a little bit more cautious. So the p.adjust function will allow you to do that. And so you'll just provide it a vector of your p-values and then put that into that p-adjust function. And you can choose different methods of adjustment. So there's a Benjamini-Hochberg approach and a more conservative approach called Bonferroni. And you can choose from a number of these different corrections. But this is a good idea to do if you're running multiple tests. So just keep in mind that function is p.adjust. All right. So there's a number of other statistical tests that you might be interested in checking out. Definitely use that question mark followed by the test name for information about it, or, refer to our resources on the website if you're curious to learn more. So there's that Wilcox test. It's a kind of version of a t-test with fewer assumptions. Our Shapiro test for testing whether you're meeting normality in your distribution of your data. We've got a Kolmogorov-Smirnov test, Fisher's t-test, a test for variance being equal or not, chi-square test, and analysis of variance. So any of these, definitely pretty straightforward to do in R, but definitely check out the documentation if you're curious. All right. So we use core to calculate correlation between two vectors. Core.test can give more information. Personally, huge fan of core plot for quick visualization of correlations. And as I so nicely demonstrated, you have to use the correlation matrix for that. So run core first, take those results and put them into core plot. Your t-test one sample test will test the difference in mean of a single vector to see if it's different from zero as one input. And a two sample t-test is going to test the difference in means, so difference in two groups, and it has two inputs. The tidy function from the Broom package is useful for organizing and saving statistical test output in a Tibble format. And remember, if you're doing lots of statistical tests, that the p-adjust function is an option for doing a correction on your p-values, just to make sure you don't detect a false positive just by accident. All right, I'll pause here, see if there's any questions before we get some practice in lab. All right, got a thumbs up, maybe ready to get some practice. All right, so let's load the packages we'll need, and we'll load the CalEnviro screen data that we've been working on quite a bit and save it to the CES object. So let's go ahead and run those library functions, and we'll create an object. Okay, so I have the data loaded up, and I want to compute the correlation between housing burden and low birth weight variables in this data set. And so just taking a look at these columns and what they mean. So housing burden is the percentage of housing burden low income households. They spend more than 30% of income on rent, mortgage payments, other housing costs. And then low birth weight be the percentage of births that are low birth weight. So these are both percentages, but higher values could potentially be like a harmful impact on folks' well-being. So let's do a select to choose the columns to save as an object. We'll use the core function and then use complete obs. I'll give us a moment to give that a try. All right. So let's create a small subset. We'll do CES sub, and we'll take CES and select just those columns we want. So that was housing, and it's auto completing for me, which is very nice. Just go ahead and hit enter. And low birth weight. So those are not the percentiles, they're the actual values. Okay. So if I look at that, it's literally just two columns. So let's do correlation on that subset. All right. So we have missing values. So we're going to want to use complete observations. All right. So taking a look at this value here, looks like that's the correlation coefficient. It's not a super strong relationship, right? It's not zero, but I don't see like a huge relationship between these two variables. All right. Questions about what we were able to do with core here? All right. So let's change the code to add a few more variables. So I'm going to copy this exact code here. And so I'm going to add diesel PM. I'm going to add traffic. I'm going to add asthma. All right. So I have a much bigger matrix this time. And so I can kind of peruse this and try to see if there's variables that are kind of closely related. So looking at diesel PM and traffic looks kind of a little bit higher, maybe. Asthma and low birth weight looks kind of a little bit higher. So I can maybe even do a cool correlation plot here. Core plot of that correlation matrix. Let's spell the function correctly. All right. It's a little bit different from the last one. I want to say that there are some arguments you can give it to get rid of this diagonal, right? Because obviously housing burden is a perfect correlation with housing burden. So that's not super informative. Let me look at those docs real quick. It's been a minute since I looked at that. Let's see. Diag is false. Let's try that. And so many options here. Let's do type is upper. All right. There we go. So questions about the correlation matrix or the plot. We feel like that's making sense. Yeah, that's a good question. It gets rid of the one-to-one line. So each variable compared with itself is a perfect correlation. But that's that's not really like giving us new information. So we can get rid of that. By default, it's in there, but we can remove that. All right, I'll give us a minute. So I kind of copied this down if we need to, and then we'll move on. Okay. So up next, we'll want to perform a t-test to see if there's a difference between low birth weight percentage in Los Angeles compared to San Diego. So we'll want to create a subset where county is Los Angeles, create a subset where county is San Diego. We'll pull that column for both subsets and then use t-test to compare. So let's break this down. Let's start kind of incrementally here. So that first part, we'll do a subset where we do CES, and we'll remember how we filter, right, to create a subset. So let's do California County is Los Angeles, and then San Diego is the same thing, just filtering differently. Okay, so I've got my subsets. So I've got like 2,000 census tracts in LA and 600 some in San Diego. Okay, so I have my subsets. Those are the first two items. Let's take those and pull. Let's go. The X variable is Los Angeles. Pull that low birth weight column. Okay, so remember this is going to be our vector, right? It's just numbers. And then our Y will be San Diego. Same column. So we made some subsets, right? So if I were to kind of like check these out in my environment, I have 2,000 some rows for LA and 600 some rows for San Diego. So let me kind of mark these up here. So subsetting my data for the census tracts just in those areas. Okay, but for the t-test, we want to pull out a column into a vector. So let's create a vector X where it is Los Angeles, and we're going to pull that low birth weight column. All right, so that is now, I've got that over here as a vector in my environment. So right here, just simple numbers. And then for our other group, do San Diego and do the same thing. We're going to pull out that same column because we want to compare the two groups. All right, so same structure. One is a little bit shorter, right? That's okay. So I've pulled the column for both subsets. And so now let's get into the fun stuff. Let's use t-test to compare the two vectors. So I'm going to do t.test. For our first group, we're going to supply X. And for our second group, we're going to supply Y. All right, so our alternative hypothesis is that the true difference in means is not equal to 0. We're trying to say, is the birth weight in Los Angeles different from the birth weight in San Diego? And so what I can see here is the p-value is very small, which is a good indicator that I can reject my null hypothesis. I feel pretty good that those groups are different. And if I'm curious about the mean of X, so the birth weight mean for LA is 5.31%, our low birth weight. And then in San Diego, only 4.6%. So yeah, a little bit lower in San Diego. If I wanted to kind of clean up these results, I could use tidy from the Broom package and get a nice little table. And you can see here estimate 1 for LA and then estimate 2 for San Diego. All right, so let's talk a little bit about regression. So we talked about correlation, t-tests, all that, but regression is going to be a super powerful method to be aware of. So linear regression is a method to basically look at the relationship between some response, so our dependent variable, and one or more explanatory variables or independent variables. And actually, fun thing to think about or important to think about is that so many statistical tests are actually specialized regression, including t-tests. So again, very important method. And, once you get more advanced in data science, I feel like sometimes, folks look at regression like it's a little too basic or, a introductory method, but I think it's actually super powerful. And so many more advanced methods are based on it. So very powerful method to understand how to use, and definitely great for a lot of applications. All right. So let's talk about the notation a little bit. Promise we'll try not to get too much in the weeds of the math side of things. But a linear regression is basically, you can boil it down to a little bit of an equation, right? So we're looking at some kind of outcome, right? We want to see what kind of independent variables might affect some outcome down the road, right? And so that outcome is typically denoted as y, and it's a value that is determined by some kind of value that is an intercept in a line, basically, and then some kind of slope indicated here. And so, what are all these elements meaning? So, yi is the outcome for person I. So it's saying, all right, well, maybe you're doing a clinical trial or something like that. And yi is the outcome for, or y1 is the outcome for person one, y2 is the outcome for person two, and so on, right? There are tons of different values. Alpha is going to be the intercept, and that's the same for everybody. Beta is the slope, so also called a coefficient. And this is basically the change in y that we'd expect for every unit change in x. So every time some independent variable x increases by 1, how much does y increase? What's the relationship between the two of them? Xi is the predictor for person I. So basically, we're thinking about y1, y2, y3. X1, x2, x3 is the corresponding independent variable. And so maybe that could be the dosage of some treatment that we're giving to get some outcome. And then there's always variation and error in the data that can't really be explained quite yet by that variable. So the residual variation is like the leftover variation, what we would call, for every person as well. Okay, so that gives us our equation for our linear regression. And so a little bit better way to visualize this perhaps is the line that is measuring some kind of pattern here. We've got intercept alpha with the blue dot. Our coefficient or our beta is measured with the change in basically the rise over run. So change in y over change in x with the green lines here. And then any residual error. So how far is the dot that we're observing? How far is that from that line that we're trying to use to predict values, right? So the error for this dot, for example, right? That error is going to be a little bit larger than this one, right? That one fits the line really nicely. And so that varies by observation. Okay, so that is how things will look when we have one independent variable. But obviously the world is complex, right? There's multiple things that could affect an outcome, right? Somebody's in a clinical trial and, maybe the time of day they got the treatment matters, maybe how old they were affects how good their outcome is. Like lots of things about the subject, about the particular treatment might be important. So we want to accommodate all of that, or as much as we can, as much data as we think is appropriate. And so we can continue to add on those variables. So we just had one beta before, but let's imagine we have a scenario where we have lots of independent variables. We can have multiple betas. And so usually that's denoted with a plus sign here between the different betas and the different independent variables. And so just like before, yi is the outcome for person I, alpha is our intercept, but a little bit different. We have, if we have 3 independent variables here, we have beta 1, beta 2, and beta, this should be 3, sorry about the typo, they are the slopes or coefficients for those different variables. And so that will be basically measuring the difference in y for a unit of x while accounting for those other variables, right? So These are really nice, maybe if you want to account for the confounding effect. I mentioned, age or time of day might affect a treatment. And so that would allow you to measure the effect of some treatment on an outcome while accounting for age, while accounting for time of day. So sometimes we want to mostly just get rid of additional confounding variables. Okay. And then the independent variables are denoted in X for each person I. And then there's, again, residual variation. So just mentioning the distance of those points to the relationship that we're measuring. And definitely can check out more detail with the case study here. All right. And so with that background being said, let's think about how we would fit a regression model in R. So typically we're going to use the function GLM, and this is generalized linear model is what this stands for. You might also see LM, which is a little bit more limited function. It performs very similarly, but only allows for normally distributed error. So basically typical linear regressions, GLM is going to be a little more flexible and allow you to draw from different distributions. And so we typically provide two arguments when we're working with GLM. We provide a formula, which is basically that equation. So this thing right here, so that's our formula. We'll provide that formula, and it's going to be using names of columns in our data. So that's how we point to those value variables. And the data, where is the tibble or the data frame that we want to pull those columns from. And so luckily, writing out that formula in R is actually pretty straightforward, right? This looks pretty complicated, right? Like there's subscripts and there's Greek letters, like it's a little scary looking. However, this is going to translate to Y tilde X in R. So a little bit more straightforward. All right. And so in practice, Y and X are actually replaced with the columns from our data set. So as an example, let's say we want to fit a regression model where the outcome is income, right? We're trying to predict income, for example, and the predictor is years of education. So our formula would be, given these two columns of our data set, would be the outcome on the left, that's the income, and the predictor, which is years of education. So typing those column names exactly as they appear in the data set. When we have more than one independent variable, all we have to do is separate them by plus signs to add them to the model. And so again, these are the names of columns in our data set. And so with the previous example, we're looking at an outcome of income, and we want to predict it using years of education, but also age and location, right? We think those variables might be important to determining income. And so here's what our formula would look like. We've got our outcome here on the left, and that's a effect with the tilde. That is an effect of years of education plus age plus location. All right, so let's look at an example, and we'll look at the heat-related ER visits in Colorado. This data set's like slightly different. It's got age groups in it, and so it's separated out by age category. And we'll actually combine this with another data set that has some weather information about temperatures, right? So we know how many folks were visiting the ER, but we want to try to predict that maybe using some climate data. And we'll use this Denver temperatures as a proxy for the state of Colorado. All right. So let's read in the ER data from this URL. We'll do our handy read CSV function. All right. ER looks good. And temps is going to be from this URL. Read CSV with the link. All right. And I want to combine them. So I'm going to actually join these data sets using full join. So ER temps together, it's going to be full join ER and temps. Okay, it's joining by year. I think that's what I want to do. So for example, temps, just one observation per year. All right, so let's take a look at this data set. So I've got different years, I've got different age categories, and then visits to the ER for heat-related illnesses, and then the highest temp in that year, and then the number of days above 100. So like for 2012, looks like there were 13 days above 100 degrees Fahrenheit. So those are pretty hot, or that was a pretty hot year, right? So maybe we expect more ER related visits related to heat illness. So basically, poor health outcomes related to that. So let's explore this a little bit more. All right. So for this model, we're going to use two variables. We're going to see the number of visits for the ER for health-related or heat-related illnesses, and we're going to use highest temp, so the highest recorded temperature of the summer. And so if we're trying to think which one is our outcome and which one is our predictor, I would think that visits would be our outcome, right? Because, hypothetically, temperature being higher would result in more visits and not the other way around. More visits doesn't make the temperature higher. So let's consider this our outcome, and let's consider this our predictor. So let's create a object called fit, and we'll use the GLM function. So we'll say, all right, well, I want to use the data set ER temps, and I want my formula, go back here to the beginning here, I want my formula to be visits is predicted by highest temperature, I think. Yeah, highest temp, and separate those with a comma. All right. So fitting that model doesn't take very long, it takes just a second or two, and we can take a look. All right. So we get some idea of what our coefficients are. So what is our intercept value and what is that beta value? And this is pretty much all we get with just looking at the fit. But the nice thing is we can do the summary function. Remember, we did that in Summarize. It kind of gave us details on the mean and the median and all that. But we could also use that on a model fit. So we could do summary of fit and get a little bit more information. So I not only get the coefficients, but I get the p-values as well. All right. And so how I might interpret this is that I'm not seeing a very small p-value for highest temperature. So I'm not sure that that's a great predictor of ER visits. Okay. And just like with t-test and correlation, the Broom package and the tidy function can help us clean up those results a little bit as well. And so how I might interpret this is that for every 1 degree increase in the highest temperature, we see a 1.134, basically 1.134 more heat-related ER visits. Okay. So that would be the coefficient, that estimate there. Okay. And just looking at the error, this is pretty big, right? So I feel like we don't have really good confidence in this predictor, right? This relationship, it's going to be, not so significant. It's got a pretty high p-value, as I mentioned, right? And taking a look at the statistic here, or the error here, thinking about plus or minus 3.32, right? We're not very confident in how much every 1 degree in the highest temperature, we're not really confident in how many more heat-related ER visits there are. So we could try to use highest temp to predict visits, but it's not a great predictor. All right. So, maybe if that's not a great predictor, maybe we could try some other variables. Maybe some other things would be more helpful in explaining the number of visits. So let's take a look at adding the year. So we'll take this GLM here. Let's just go ahead and add the year. We'll run that, the fit, and then the summary of the fit. All right. And so notice I have another line in my output here. And again, we could use Tidy and Glimpse to view that output a little bit more nicely. Okay. And so taking a look at these results here, taking a look at year, that p-value is just under 0.05. And so what this tells me is maybe the particular year, that year had some heat waves or something like that, that's a better predictor than the temperature itself. So the attributes of that year could be more important. Right. So you could interpret it either way, right? Like you could interpret it as we're trying to understand the effective year while accounting for temperature, or the effective temperature while accounting for year. It's depending on what what estimate you're more interested in reporting. Yeah. So, year is a little interesting here, right? Because we're treating it as a number. And so what you could say is like over time, years increasing, right? It's going from 2010 to 2011 to 2022. And so how I would interpret this is that as you go forward in time, there seem to be a little bit more ER visits because that's a positive estimate. And so while that is an outcome we see for year while accounting for highest temperature as well. Other questions about how this works and how we put this together? All right. Okay. So that's actually a great transition to talking about categorical data, right? So we looked at some numbers. Years, we're treating it as kind of continuous, which maybe not appropriate. Maybe we'd want to treat it as a category. So factors are getting special treatment in regression models. And what I mean by that is that the lowest level of the factor is actually the comparison group. And we're looking at all of the other factors relative to the first one. And so let's say we want to add age as a category into our model. You could say maybe different age groups have different rates of ER visits. And so we'll want to convert that into a factor. And so how we would do that is, as Carrie described yesterday, we could use the factor function. So we could do just mutating that age column. We're not actually changing the data, but changing the class. So we'll take that data set, we'll pipe that into mutate, and then take age as a factor of that existing column. If we take a look with Glimpse, we should see that age is a factor. And each of these categories, it's like 0 to 4 years, I believe 5 to 14, then 15 to 34, et cetera. All right. And so then including age as basically a categorical variable in our data, could go ahead and add that on here. All right. So now, in addition to highest temp and year in our data set, we now have accounted for and added the effect of age. So I have these different age categories, but you'll notice I don't have that category for 0 to 4, right? So if I take a look at my data set and I want to look at the different categories of age, I've got 0 to 4 and then my other age groups here. And so all of these ages are in comparison to the existing group. So what it looks like to me is that there are more visits for these older age categories. They're all positive, all more visits compared to that 0 to 4 age range. And that could just be that there's more of them. So maybe the rate would be more helpful here. Okay, so here's where reordering our age groups might come in handy. We can re-level the factor as we saw yesterday. So maybe we don't want 0 to 4 years to be our comparison group. Maybe we want 65 plus to be our comparison group. So if we reorder that factor, notice that the age groups here are a bit different, right? So I could see that 35 to 64, 15 to 34 have more visits total among them than the 65 plus category, but the 65 plus category has more visits than 5 to 14 or 0 to 4. So really just depends on what you want that baseline to be. All right. And so I don't usually recommend this, but you can view all the groups if you remove the intercept, but it does make interpretation a little bit of a challenge. So you can add that with a -1 in your formula. Okay. So want to say one final topic related to your linear regression formulas, and that is interactions, which are a little bit of a tricky topic, but can be really important. And so the way I like to think about it is that the relationship between two variables depends on a third variable. So we could imagine a scenario where we are trying to bake a lot of good quality cookies. And when our oven is at low temperature, we get more cookies if the time we bake the cookies is a little bit longer, right? So taking a look at this column here, if temperature is low, yield is quite high when the bake time is long. However, if we go over here to high temperature, our yield is going to be higher when we have a short baking time, right? If we have a long baking time, lots of those cookies might be burnt, right? And then lots of them might be undercooked at low temperature, right? So how much yield we get really depends on both of these variables. The relationship has an interaction. Okay, so how we do this in R, we were adding plus signs to basically to add variables. But if we want to indicate an interaction between variables, we can do that with a star. So this asterisk symbol. So basically allows the slopes to vary with regard to the interacting variable. So what we'll get is not only those variables by themselves, but also an interaction between highest temperature and the age group. So basically saying the effect of highest temperature depends on which age group you are looking at. All right. And another way to visualize this, I think oftentimes it's easier to just look at a plot of it, right? So how we might do this is by plotting two variables, so highest temp and visits, but then having different age groups in different colors. And so what I might be kind of noticing here is, I don't believe it was significant, but taking a look at this 35-year category and the 15-year category, it looks like visits increase for this group with higher temperatures. However, we take a look at the 0 to 4 category, it doesn't seem like the number of visits really is affected that much by higher temperature. And I think maybe that makes sense. It could be that, very young kids are not doing a ton of, laborious work outside or something like that. Maybe they're inside a little bit more. So we might kind of explore that more. All right. So GLMs are going to allow us to also fit regressions for non-continuous or non-normal outcomes. So these are things like logistic regression or Poisson regression. And so we can allow the GLM function to do that by adding the family argument. And so that's going to describe the distribution of that error term and the link function to be used in the model. So these typically, like the most used one here, are you could specify that family is binomial if the outcome is binary. And so, you have your predictor variable is like, did they visit the ER or not, true or false? And then Poisson could be the outcome is count or rate. And so important to use the right test and think about kind of that distribution, kind of what is the distribution or what kind of data do you have as your outcome variable? And you can check out this case study for a little bit more about that. All right. And so let's look at a logistic regression example. We will use the same data set and let's create a new binary variable called high rate. And we'll say that a visit rate of number of visits, visit rate more than 8 qualifies as a high visit rate. So what we could do is take the data set, create a new column, high rate, where when rate is greater than 8, it will be true. Otherwise, it will be false. So you can kind of see a preview of that column here, but let's actually create that. So ER temps, we will use the mutate function to create high rate column. And so when rate is greater than 8, it will be true. Otherwise, it will be false. So if we take a glimpse at ER temps, you'll notice I have some falses and trues. It's a logical column. So this is going to set us up really nicely for logistic regression, right? The outcome is binary. All right. So how do we do that, right? We've been working with this formula where we've been using highest temp, year, age to try and predict the number of visits, but maybe now we're trying to predict a high rate of visitation. So we could do same as we have been doing, where we have done GLM, and we're predicting high rate as an effect of highest temp, year, and age, where the data is ER temps, and the family is binomial with a logit link, right? So indicating that the outcome variable is binary. All right. So looks like that ran okay. But I might want to get the summary again. So let's save that as binom fit and get the summary of binom fit. All right. So not a whole lot that is a useful predictor of a high visitation rate, but we could, conceivably put this together just to try and do some exploratory analysis. All right. And feel free to check out this case study for more info. Okay. And then last topic I wanted to mention really briefly is odds ratio. So this is very common to do in epidemiology, but odds ratio is a measure of association between some exposure, right, and some outcome. And so the odds ratio is going to represent the odds that some outcome will occur given a particular exposure compared to the odds of the outcome occurring in the absence of the exposure. So, let's say you were potentially exposed to the flu. What's the likelihood, given you were exposed to the flu virus, what's the odds that you will have an infection versus not? And so you can use the odds ratio function for X and Y, and that comes from the Epi tools package. And so how does this look like? And so what we might do is, in this example, is acknowledge that during the years of 2012, 2018, 21, and 22, there were multiple consecutive days with temperatures above 100 degrees. And we'll code this as heat wave. And so when year is in that list, heat wave will be true. Otherwise, it will be false. And so we have down here now two binary variables where high rate is, high visitation rate to the ER, and heat wave is true if there was a heat wave that year. Okay, so we're calculating the odds ratio for whether a heat wave is associated with having a visit rate greater than 8. And so our response might be the high rate values. So I could pull out that column. And our predictor is the heat wave column. And so what I want to do is plug that into odds ratio, the predictor coming first. So heat wave is first and response is second. And so I can get my contingency table from that, as well as p-values. And so how would we interpret that? So we look down here, the odds ratio is 3.8855, 3.86 basically. And so when the predictor, the heat wave year, is true, the odds of the response or the high hospital visitation basically are 3.86 times greater than when it is not a heat wave year. All right. And some final notes. It's important to understand the statistical methods that you're using, any underlying assumptions, and then correct interpretation of the method's results. And it's also your responsibility, if you're exploring this stuff for research, to understand the R software, right? Like understanding the arguments and the defaults and what's that going to mean for the outcomes that you get. All right. So to summarize, we talked a lot about this GLM function, which is going to fit regression models. You would use the formula argument to specify the model. This would look like, y tilde x with the y's and x's as stand-ins for column names. You use data to indicate which data set you're taking those values from. And you can use family to do other regressions like logistic or Poisson regression. And then summary is going to be a really nice way to give you more statistics from just the fit itself, right? So the outcome of GLM doesn't give you very much printed to the console. Summary is going to give you a little bit more info. And then if you're interested, this is something that you might use in your work. Odds ratio is a really nice function for getting your odds ratios. And that comes from the Epi tools package. And this is just the tip of the iceberg. There's lots of statistical tests out there, right? So it really will depend on kind of what you're interested in and what is a common practice in your field and that kind of thing. There's lots more resources on the website, of course, but also checking out the chapter on modeling in the Tidyverse book. There's a nice cheat sheet here for when to do what test, and also open case studies. It has a lot of info about different tests. All right, so I'll pause here if there are questions. Otherwise, we will continue our practice. Yeah, sure. We can go back to logistic regression. Which slide was that? All right. So I would say that, taking a look at these p-values, that not very many of these are good predictors of it being a high visitation rate year or high visitation rate value, right? So we created that column when rate was greater than 8, it would be high visitation. When it was lower than 8, it would be low. And so what we're trying to do is say, do any of these variables predict that? And I would say that it doesn't seem like that's the case. Yeah. And then, not just the p-value, but just taking a look at the estimates and the error on the estimates. So for example, like this age group, right? Its estimate is, negative, but like there's quite a large error on that. So not super confident in that estimate. Other questions? It's not just like, that far off from correlation, right? But it's the coefficient, right? Like if we think about the rise over run, it's it's talking about how much change in that variable will result in a change in the outcome. Well, let's get a little bit more practice. And of course, if there's other questions, like feel free to chime in the lab. I know it can be a little bit of a scary topic. So thanks for hanging in there. All right. So we want to fit a linear regression with low birth weight as the outcome and housing burden as the predictor. We'll save that model fit and then display the summary table. So I'll give us a minute to see if we can get something down. Okie dokie. So if we're doing a linear regression, we'll probably want to use that GLM function. And we got to supply the formula and the data, right? So it's told us that we want low birth weight as the outcome. And the outcome is going to be on the left. It's predicted by housing burden. Then I have to tell it that I want to use the CES data. All right. So that gives us output, right? So it gives us an estimate of the slope here, or the coefficient. But I'm going to save this and actually use the summary table because I think it's more informative. All right. So I should get some outcome that looks a little something like this. All right. So thinking about how we might interpret this. So this estimate is positive. So I would think that increasing housing burden leads to increasing percentage of low birth weights. So that does make sense. And then the p-value is quite low, right? It's quite small, which tells me that, we feel pretty confident that there's a relationship here between housing burden and low birth weight. Basically, this is a good predictor of these values. The error is pretty small. Okay. And so we might want to take a look. If we're going to add another predictor, we could just copy the code we have here and save that model fit in another object and display the summary. So let's take this code here and we'll add traffic as a predictor. We'll save that as linear model fit birth weight 2 and then do the summary on LM fit birth weight 2. All right. And so how might we interpret this? So similar as before, housing burden still is a pretty good predictor. It's got a low p-value, low error, and high t-value here, or statistic. But taking a look at traffic, the p-value is a little bit higher, right? That statistic is a little bit lower, right? So I would say that's not as good of a predictor of low birth weight percentage. So maybe the kind of pollution caused by traffic is not directly doing anything or not directly related. And so one thing to point out too is this statistic down here called the AIC. There's a lot of ways to measure quality of a model. So you may be wondering like, okay, well, should I report this one or should I report this one up here? And so one thing you can do is look at the AIC value to compare. Like typically we'll want a smaller value. So this model was AIC of 28526. And this one up here was 28611. So typically the smaller this value, the better the model. So it's saying this model is ever so slightly better. It's not dramatically better, but it does a little bit better job of accounting for variation in the data. We could do one more thing. We could try to make this an interaction to say, all right, well, maybe the effect of traffic on birth weights depends on, whether you're housing burdened or not, right? Maybe they are not independent of each other. All right. So I don't really see that is the case. Maybe ever so slightly showing an effect of traffic, but the model is not necessarily that much better.